When beta-carotene is oxidized in vivo, it breaks in half and forms molecules of retinal, vitamin A, which is a precursor to the pigment in retina responsible for vision. The conjugated system of retinal consists of 11 carbon atoms and 1 oxygen atom. In the ground state of retinal, each level up to n equals 6 is occupied by 2 electrons. Assuming an average internuclear distance of 140 picometer, calculate the separation in energy between the ground state and the first excited state in which one electron occupies the state with n equals 7 and the frequency of the radiation required to produce a transition between these two states. How does the absorption spectra of linear molecules shift with number of conjugated atoms? The structure of beta-carotene is given. So we can see that beta-carotene is conjugated, but the problem is concerning with vitamin A or retinal. This is the structure of retinal. If we count the number of conjugated atoms, we can start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 atoms involved in conjugation and there are 11 bonds. So to solve this problem, we need not know the structure of retinal because all we need to know is the number of atoms in conjugation and the number of bonds in between them, which is given to us. Any conjugated system can be modeled as a one-dimensional particle in a box. This is because the conjugated system is linear, so we can assume that it's a one-dimensional. For one-dimensional particle in a box, energy is given by E equals h squared n squared by 8 ml squared, where L is the length of the box, m is the mass, and n is the energy level. And h is Planck's constant. The ground state of retinal, each level up to n is equal to 6 is occupied by 2 electrons. We have to find out the separation in energy between the ground state and the first excited state when the electron occupies n equals to 7. Highest occupied level is n is equal to 6 in the ground state. In the excited state, n is equal to 7. So we have to find the difference in energy between the n is equal to 7 state and n is equal to 6 state. So delta E will be equal to E of n plus 1 minus E of n, which is h squared n plus 1 squared by 8 ml squared minus h squared n squared by 8 ml squared. If we take h squared by 8 ml squared outside, we can have n plus 1 squared minus n squared. This will be n squared plus 2n plus 1 minus n squared which is h squared by 8 ml squared times 2n plus 1. So this will be the delta E between E of 7 and E of 6. H is Planck's constant. which is 6.626 times 10 to the negative 34 joules second. Mass of the electron is 9.1094 times 10 to the negative 31 kilograms. Energy level is 6, which is the highest energy level of the ground state. The average internuclear distance equals 140 picometer. Since we have 11 bonds and the distance of one bond is 140 picometers, the distance of 11 bonds would be 11 times 140 picometer. The length of the one-dimensional particle box would be 11 times 140 picometers, which is 11 times 140 times 10 to the negative 12 meters, because 1 meter is 10 to the negative 12 picometers. This gives us 1.54 times 10 to the negative 9 meters. Now we can plug in the values. E equals h squared, which is 6.626 times 10 to the negative 34 joules second, times 2n plus 1, which is 2 times 6 plus 1, over 8 times 9.1094 times 10 to the negative 31 kilogram, times 1.54 times 10 to the negative 9 meters square. Solving for this gives us joule squared second squared over kilogram meter squared. Let's look at the units. Joule is units of energy, which is force times distance. Units of force is mass times acceleration. So units of joule is kilogram meters per second squared times meters, which is kilogram meter squared per second squared. Now plugging this into this, we get kilogram meter squared per second squared, the whole square times the second squared divided by kilogram meter squared. This gives us kilogram meter squared per second squared, which is the unit of joule. So we get 3.30 times 10 to the negative 19 joules. The second part of the question is, we have to find the frequency of the radiation required to produce a transition between these two states. To find that, we can use E equals h nu, where nu is the frequency. So the frequency of radiation required to produce the transition between the two states would be delta E. So nu equals delta E over h. By substituting the values, we get 3.30 times 10 to the negative 19 joules over 6.626 times 10 to the negative 34 joules second. This gives us a value of 4.98 times 10 to the negative 14 per second. How does the absorption spectrum change with the number of conjugated atoms? We saw that delta E equals h squared over 8 ml squared times 2n plus 1. So we can see that as the energy level increases, delta E increases, and as the distance of the one-dimensional particle box increases, the energy decreases. The distance of the one-dimensional energy box is directly dependent on the number of conjugated atoms. So if the number of conjugated atoms increases, delta E would decrease. Since delta E and frequency are directly proportional, we can say that as number of conjugated atoms in the system increases, the frequency will decrease. Two different conjugated systems with length L1 and L2 such that L2 is greater than L1 because L2 has greater number of atoms in the conjugation than L1. Let's look at the waves in the energy levels. If this is n is equal to 1, n is equal to 1 will have 0 nodes because number of nodes is energy level minus 1. So n is equal to 1 will look like this for L1, and for L2 it will look like this. If you come to n is equal to 2, it will have 1 node, so that will look like this for L1, and for L2 it will be like this. Similarly, for n is equal to 3, you have 2 nodes, so it will be like this. And here, like this. So we can see that as the length of the conjugated system increases, the wavelength is increasing and the frequency is decreasing.